Okay, so this is for Physics 5B, summer 2020, and I'm at Sac State right now, and it's like completely deserted here. But this is on chapter 23.1. I want to point out a few things here. So if we go to our page, the modules, okay, so online worksheet number 8, which is this one way down here. Okay, so it's up. It's got solutions to a lot of the problems there. Okay, so we're only covering, so we got these sections in chapter 23, 1, 2, 5, and 7. In chapter 24 and 25, we're only covering the first 3 sections. And the problems are extremely easy, and we'll go over them. This video, we're just going to do chapter 23. Then tomorrow, I'll do a chapter 24 and chapter 25. And so, basically, you can download this right now. There it is in the modules. Hold on. So there it is in the modules. And then we've got the equations for chapter 23, and then I combined them for chapter 24, 25. They look like this is 23. Okay, we're not going to cover this. Okay, we stop right here. Okay, we're not going to cover this. And then 24, 25, I don't know if I have that open. Yeah, I do. So that's just reflection and refraction. Not very difficult stuff at all. Okay, so there's the 2 new equations, and then I've got and everything's final. I'm not going to add anything more at all to this. Okay, so this is all final. This is it. No new material. You got the chapter 23 PowerPoint, then chapter 24 and chapter 25. You can look at those. I'll put the videos up for those tomorrow. Okay. I'm at Sac State, so the videos are loading a lot faster here, I believe. I remember loading videos way back in March before they really shut down the campus and told us they didn't want us on campus. And at that time, the videos seemed to load a lot faster than they do for my home computer. My home computer's not, the internet's not working anyway, so I'm stuck at Sac State. All right, so here is PowerPoint for chapter 23. Okay, this one talks about induced EMF and the magnetic flux. Okay, we have seen that a current can induce a magnetic field. B field is short for magnetic field. Therefore, by closing the switch, we induce a B field around the wire, including in the loop, the top loop wrapped around the iron. So here is what we're doing. We're closing the switch right here. And when we do so, there's a current that goes through here. Now, there's that loop right there. That's going to generate a magnetic field. There are electrons in this iron, okay? The electrons do not like changing magnetic fields, but because they are charged particles, they have the power to start to move as a group, as a team, and generate their own magnetic field to try to cancel out the change. They don't like change. They don't mind magnetic fields. They just don't want the magnetic field to change on them. So what they will do, as soon as you, like right now, when the switch is open, it's the Earth's magnetic field. That's all they're experiencing, just the Earth's magnetic field, right? So they're happy, Earth's magnetic field. You close the switch, that changed the magnetic field here. And so they start to move to try to make it back to where it was just the Earth's magnetic field. So they induce a back magnetic field, a back EMF, to try to cancel out the change that you imposed on them. And that'll show up over here. The little needle will go one way or the other, because what's going to happen is that's going to cause a magnetic field down here, and that'll induce a current in this guy. Okay, so you got changing currents, you got changing magnetic fields due to changing currents that induces another current, but then that current that didn't exist before, that's a change, and now the current electrons that are in this guy will try to cancel out that change. Okay, so basically that's what's going on with this. All right, so, but the electrons in the iron do not like you changing the magnetic field, and since they have charge, they can make their own current to produce a magnetic field that cancels out the change you imposed on them. But this current in the iron produces a magnetic field around the bottom coil and induces a current in that wire, which we can then measure with a galvanometer. This is how basically we turn mechanical energy into electrical energy. Okay, this is how Folsom Dam works. This is how Nimbus Dam works. This is how fluorohydro, windmills work. This is all that stuff is just mechanical energy into electrical energy. And the mechanical energy would just be keep pushing that up and down, up and down, up and down. If you pushed it down and left it down, and the magnetic field stayed the same right here, then the electrons would stop flowing together, right? There wouldn't be a net current anymore because they get used to the new world order. So you got to keep changing it. Okay, induced EMF and magnetic flux. An EMF, we talked about that before, it's a voltage. It's called electromotive force, but it's not a force. You can think of the electrons being forced through, but it's a voltage. It has units of volts. And thus an EMF and thus a current is produced in the if the magnet is moved. Oops, that should be if. If the magnet is moved relative to the coil or coils is moved relative to the magnet. Okay. So let's see. An EMF and thus a current is produced if the magnet is moved relative to the coil or the coil is moved relative to the magnet. It doesn't matter either way. As long as there's the coils experience a changing magnetic field, the current's going to be induced. It doesn't matter whether the magnet moves or the coil moves relative to the magnet. In other words, it doesn't matter if the magnet moves relative to the coil or the coil moves relative to the magnet, that's still motion. The direction of the current depends on the direction the magnet is being moved, into or out of the coil. You can see here they're moving the magnet into the coil. They're showing you the direction of the current. Here they're moving the same magnet. They're putting north in here. They're taking north out here. And you can see the current's going in the opposite direction and so on. And they do it for south and so on. Then if it's stationary, no current, because the electrons have gotten used to that new magnetic field. They don't care anymore. They just don't like change. They just like things to stay constant. If the magnet is not moved, the electrons adapt to the new magnetic field, and as long as it stays static, no current will be induced. So movement and the changing magnetic field is the key. Okay, induced EMF and magnetic flux. Place a loop or a coil, okay, you could have more than one loop, in a magnetic field and turn it. So right now you're here cranking this right here, and this causes this guy to turn. So we're not changing the magnitude of the magnetic field, but we're changing basically the flux. We're going to call it the flux through the area here, okay? Here we are converting mechanical energy, you're turning the switch, into electrical energy, the current that starts to flow in the circuit. This is known as a generator. This is how generators work. This is the opposite of the similar setup we had before, the electric motor, where we were converting electrical energy into mechanical energy. This is the opposite of that, okay? There we were using electrical energy to make a coil rotate. Here we're rotating the coil and generating a current in the coil. Okay, to the right is a diagram showing the basic mechanism for how mechanical energy is converted into electrical energy. In this case, it is not the magnitude of the magnetic field that is being changed. It's a set magnetic field. You got your north pole here, south pole here. That's a set magnetic field. We're not changing that, okay? But the magnetic flux from the magnetic field that passes through the area of the loop, that's what's being changed, okay? Sometimes it's maximum. Then when the area here is perpendicular to the magnetic field, but then sometimes when the area is parallel to the magnetic field, no flux goes through that area, and we have zero current flowing. By turning it, that's where you're making your AC, alternating current. By turning the loop, we are changing the orientation of the magnetic field relative to the loop. When the loop is perpendicular to the field, the maximum amount of flux passes through the loop. When the loop is parallel to the field, then no flux passes through the loop. Okay, induced EMF and magnetic flux. There's the symbol for flux, magnetic flux. Just that little guy right there. Magnetic flux in a constant magnetic field. There's how we find it. It's equal to the strength of the B field times the area times the cosine of theta. Now here's where we have to be careful. And I don't think you have any problems where this is going to be something, but there are problems where we could run into this. It's not the angle between the magnetic field and the area. It's the angle between the magnetic field and the perpendicular to the area, or the normal to the area, okay? It's this angle here that we're interested in, okay? They did it that way. They could have done it the other way, just said sine, but they did it this way. I think there's a reason for it that would show up if we got more in-depth in this. It is made a bit confusing by the fact that theta is the angle between the magnetic field and the perpendicular to the area, not to the area itself. Okay, now Faraday's law of induction, Lenz's law. Lenz's law, the EMF creates a current I and magnetic field B that oppose the change in flux, okay? So you change, again, that's what we just talked about. That's not new. You said, wait, isn't that what we just talked about? Yes, it is. It's what we just talked about. Now here's how we can find what the EMF is going to be. This is, you may see this written as EMF, or just this kind of like cursive E or whatever. Now N is the number of loops, and it's negative because remember we're inducing an EMF and a current that's opposite to the one that basically you're putting it. It's a magnetic field. It's opposite to the one that it's changing. It's opposite the change of the magnetic field. So we got the change in flux, okay, over delta T over time. The faster we change the flux over a small amount of time, the greater EMF we're going to induce. So we just plug in what flux is. We had it up here. Okay, it's magnetic field times area times cosine of theta. Just plug it into there. Okay, so we change any one of those. We change the magnetic field, we change the area, or we change the angle. Okay, we're going to induce an EMF. N is the number of coils in the number of loops in the coil. Oops. So again, changing the magnetic flux either by changing the magnitude of the magnetic field or the orientation of the coil relative to the magnetic field induces a current in the coil. This current generates its own magnetic field which seeks to cancel this change. All right, now here we've got basically the ideas are these transformers. Transformers make use of this. So at the power station, they put out 12 kilovolts, okay? So the power, we can assume the power is pretty close to the same. Power equals current times voltage. So you got 12 kilovolts, you got so much current. The problem is we want to reduce the current. How do we reduce the current? We up the voltage. So you see we started with 12 kilovolts. Now they stepped up the voltage through here. This is the transformer here. So by the time it gets to here, right here, it's 400 kilovolts. I don't know why they're showing it way over here, but it's 400 kilovolts here. The transformer stepped up the voltage and stepped down the current. Then it gets over to this transformer, and then this one is going to step down the voltage and step up the current because we're getting ready to get to your house. So they got it down to 13 kilovolts. So they stepped up the current, but they want to step down the current because you're losing energy because of the current. We'll talk about that in a second. Now here you got a transformer that's sitting on a pole. You probably looked up and saw those things and wondered what those were, with those trash cans on the top for the telephone guys to throw their trash away or whatever. No, they're transformers. And that one's going to step down the voltage down from 13 kilovolts down to 240 volts. And so that will cause the current to go up, which is what you want it to do, okay? So this is the whole process we go through. Now, so we've already seen the basics of how an electric generator works by physically turning. You know what? I think this guy's in the wrong place. Hold on a second. Okay, I've already uploaded the newer version of this. I just did that. So unless you downloaded this PowerPoint within the last 30 minutes, you should have. I mean, it's 5:25 right now. So if you downloaded this before 5:25 p.m., which I doubt anybody did, because I don't think anybody even realizes it's up there yet, then you got to download this one. I just fixed it because I think I have the slides in the wrong order. Okay, 23.2, Faraday's law of induction, Lenz's law. Lenz's law, the EMF creates a current I and a magnetic field B. So we did this. Yeah. Didn't we not? So again, changing the magnet. Yeah. Wait. Lenz's law, yeah. So we talked about this already. N, change in flux over change in time. N is the number of loops. So again, changing the magnetic flux either by changing the magnitude of the B field or the orientation of the coils relative to the B field. Yeah, we covered all this. This current generator. Yeah. Okay, this is where we want it to be. 23.5, electric generators. We have already seen the basics of how the electric generator works. By physically turning the loop in the magnetic field, we induce an EMF in the loop. Okay, so the EMF basically is going to be, this is the number of turns, this is the magnetic field, this is area, NBA, National Basketball Association, but here it's number of turns, magnetic field area. And then this is the angular velocity. Okay. And we've got sine of theta. Theta is also equal to the angular velocity times the time. So E equals NBA angular velocity sine angular velocity times time. Okay, N is the number of loops in the coil has. B is the strength of the magnetic field. A is the area of the loop. Or omega, I'm sorry, omega is the angular velocity of the loop in radians per second. And then we could also, all the problems, since we didn't get into this is hard to adjust to this doing stuff online instead of in class in person. But we didn't get into much on this, so we're not going to worry too much. We're just going to talk about the maximum voltage, okay? So in other words, when sine of omega t is equal to 1, okay, that means you just have, when this is equal to 1, you just have the EMF equal to NBA omega, okay? So we'll call E0 the maximum it could be equal to NBA omega, where it could be at any different time would be equal to E0, which is NBA omega times sine of omega t. Okay, you may be given an angular velocity in revolutions per minute, RPMs, or asked to find the angular velocity in RPMs. So in other words, you may start off with radians per second, and in the end they say, and then you find radians per second, but the problem says, what is it in RPMs? Or you may be given it in RPMs, but to use it in the equation, you gotta convert it to radians per second immediately. So what you do then, just here it is, there are 2 pi radians in 1 revolution. If you go around one revolution, that's 2 pi radians, that's 1 full circle. Of course, there are 60 seconds in 1 minute. So let's say we had 16 radians per second. Well, we get rid of the seconds. There's the conversion for seconds. Once we do this, we'll have radians per minute. And then we get rid of the radians here, 2 pi radians per 1 revolution. This would give us revolutions per minute, RPMs, revolutions per minute. Okay, I think this is where, and this is wrong up here. Just remember, this is wrong up here. I don't want to change, unless there's something else, bigger problem later on. I'm going to leave this as it is. This is supposed to be down here. So we talked about this already. Step up, step down transformers. Step up the voltage, step down the voltage. Step down the voltage again over here before it gets to your house. Okay, so here's the idea behind these transformers. Transformers transform voltages and currents into higher or lower values depending on what is needed. One goes up and the other goes down. Remember, we have P equals I times V. Okay, so we're going to assume the power stays pretty constant. There is some loss, but it's so small that we can neglect it. So if the voltage goes up, the current goes down. Or if the current goes up, the voltage goes down. Over long distances, there is a loss of energy in power lines called the Joule heat loss. I don't think this is in your book, but it's pretty important. All right, so, oops, didn't want to do that. So remember, one way we can show power is that power equals current squared times R. Remember, P equals I times V, V equals I times R. Plug in IR for V into P equals IV, and then you get I squared R. So the idea is to reduce the energy loss per second by reducing the current over long trips by stepping. That should be stepping. You see, that should be that. Stepping down the current. Oops, what did I hit? Stepping down the current and stepping up the voltage. Okay, I'll go ahead and upload a newer version of this thing. All right, so then I should probably change this up here. What? Oh. Okay, let me just change this. And that's not Faraday's law, it's transformers. Oh, let me up here. Okay, I've saved this version of it. So 23.7 transformers, that's been fixed. And then stepping up's been fixed. Okay, so let's see here, where are we? So on the right, oh, here we're on this picture. Okay, transformers transform voltages and currents to higher or lower values depending on what is needed. Over long distances, there is a loss of energy in power lines called Joule heat loss. Joule heat loss, power equals current squared over R. So that's how you figure out how much power per second you lose. Okay, not how much you have, it's how much you lose per second. And it depends on, so I mean, it's not power, it's energy you lose per second. Remember, joules per second, energy over time, that's power. So you're figuring out how many joules of energy you lose per second with this equation. And obviously you want that to be low. You don't want to lose a lot of energy in those transmission lines. So you reduce the current for the long travel long distance. So the idea is to reduce the energy loss per second by reducing the current over long trips by stepping down the current and stepping up the voltage. The power stays the same, P equals I times V. When the energy gets close to your home or school, then you want to step down the voltage and step up the current. I missed that down there. Step down the voltage and step up the current. Okay, on this picture over here, on the right side of the picture is a picture of a transformer. Okay, they're maybe a little bit more complex. This is a simple basic idea behind them. Typically there are two coils wrapped around an iron core. Okay, so here's one side. This is actually a P there. That stands for primary. This is where we can imagine the energy's coming in. And then here is the output. This is the secondary over here. There should be an S there someplace. Okay, typically there are two coils wrapped around an iron core. On one side is the primary coil, which is where the energy enters the transformer. On the other side is the secondary coil, where the energy exits the transformer. We assume no energy is lost within the transformer itself. There is some energy loss, as there almost always is, but in this case it is so small it can be neglected. Okay. So power into. Okay, I'm not gonna. Let's see. Power. What the heck is that? Okay, power into the primary equals power out of the secondary. So power primary equals power secondary. We're going to assume all the energy gets over to the other side. All energy per second, all joules per second get to the other side. All the energy we put in here gets over here. Okay. Now we know power equals current times voltage. So that means the current in the primary, voltage primary, equals current secondary, voltage secondary. So we solve it. We got current primary over current secondary equals voltage secondary over voltage primary. We're just rearranging this. Okay, divide through and so on. Faraday's law. Okay, so going back to Faraday's, the voltage in the secondary coil is going to be induced. Okay, remember, think again about what we're doing here. We're putting a magnetic field in this coil because we're putting current in there. We're putting current voltage there. We're generating a magnetic field. That causes a current to flow around here. That causes a magnetic field over here, which causes current and voltage over here. Okay, so that's how we're moving this voltage and current over to here. Okay, now we go back over here. So we're inducing the voltage and the current here. So the secondary voltage, that's going to be the number of turns you have in the secondary coil, how many turns we have over here, times the change in the flux over change in time. Okay. The primary coil is the same thing, only it's the number of turns we have in the primary coil. How many turns we have over here? You can see from this picture here we have a lot more in the secondary than we do in the primary. Now, the change in flux over change in time, that's the same for both. Because you're changing the flux, that gets transferred over to the other one. So they're going to experience the same change in flux over change in time. So we put these on top of each other. The change in flux over change in time cancels out. They're the same for both. And we're left, and then the minus signs will cancel out too. So we're left with the ratio of the secondary voltage over the primary voltage is equal to the number of turns in the secondary divided by the number of turns in the primary. And then we go back to this equation, but just add the last little step. Since Vs over Vp equals Ns over Np. So now we've got this right here. Okay, induction, this is what we're not going to spend a lot of time on. Matter of fact, these are things I just want you to be aware of. We're not going to do anything on them. There's no problems on these. All right, so we have already seen examples of inductance. In transformers, a changing current in the primary coil induces a current in the secondary coil. Mutual inductance is the effect of Faraday's law of induction for one device upon another, such as a primary coil in transmitting energy to the secondary in a transformer. Okay, EMF2, that's the EMF we get over here. It's going to be equal to this thing called the mutual induction times the change in the current over change in time. Okay, M is the mutual induction and indicates the effectiveness of the coupling between the coils. So maybe you want to get as much energy over here as possible. So you want to know how much energy are we going to get over here from this coil here. Okay, then we have something called an inductor. That's self-inductance. So basically, you change the current in a coil, but the coil itself induces a current and a magnetic field to try to undo the change you made. Okay, so that's called inductance, self-inductance, and it's got an L there. And then the only other thing you don't, I mean, obviously for this class you don't have to worry about it, but be aware of it. Here's a case where we put the three components that we talked about together: the resistor, the capacitor, and this is the symbol for an inductor. It's a coil. It's just a coil. Okay, there's your inductor. RLC circuits combine a resistor with an inductor and a capacitor in series. RLC circuits are important in many applications, including back, when you tuned a radio, you turned the dial, and what you were doing was changing. I believe you're changing the capacitance maybe, but you're changing something in the circuit, which causes it to tune into different frequencies. Okay, just beware of their existence. You will be doing no problems covering them. And that is it for this. Okay, so let's go over to the this guy. Okay, so the first problem. So this is induced EMF magnetic flux. This is what is the value of the magnetic flux in coil 2. There's coil 2 in figure 23.56 due to coil 1. There's coil 1. They're perpendicular to each other. See, you put a current through here, it's going to come out and go like this, come out and go like this. It's going to be parallel to the area here. That means there's not going to be any current flowing through there. So you got BA cosine. We don't have to worry what the magnetic field is or anything. It's going to be 0. Okay, that's how easy it is. And then here you've got this guy here. This guy also creates a magnetic field that looks like this. We saw those already. A current carrying wire creates a magnetic field that's going to be circular. Well, that's also going to be parallel to this guy. Okay, so remember that what we're interested in though is that perpendicular. It's this guy back up here. It goes back to. Did I pass it? Yes, I passed it probably. No, it's back here. There it is. So, see, it's the angle between the normal to the surface and the magnetic field, okay? So, if the magnetic field is coming in at 90 degrees, the cosine of 90 degrees is going to be 0, okay? So, it's the same for both. Okay, this is number 9 in Urone, an MRI, magnetic resonance. Okay, I used to know what that was. I just forgot it. Okay, an MRI technician moves his hand from a region of very low magnetic field strength into an MRI scanner's 2.00 Tesla field with his fingers pointing in the direction of the field. Okay, his fingers are pointing in the direction of the field. That means that the area is perpendicular to the field, the area of the ring. Have they talked about the ring yet? No. Okay. So find the average EMF induced in his wedding ring given its diameter is 2.20 centimeters and assuming it takes 0.250 seconds to move it into the field. Okay. So we figure out the area of the ring. Okay. And it's going to be perpendicular. Therefore, the angle between the perpendicular to the area of the ring and the magnetic field, that's going to be 0. So it's cosine of 0, which is 1. Okay, you got to kind of picture it in your head what's going on here. If we go back to these. Okay, so imagine that's the ring right there. The magnetic field is going through the ring. Okay, so it's going to be parallel to that vector A, the vector that's perpendicular to the area of the ring. Okay, so the magnetic field's going right through there, all of it. The greatest amount of flux possible, maximum flux, is going through there. So we don't have to worry about the cosine sine thing. All right, so we pull out this equation. This is supposed to be the EMF induced. Now I got it as an E now. Number of turns, okay, change in the flux over change in time. Well, we know that the flux is going to be equal to BA cosine theta, but cosine of theta is 1, so we just have to worry about the BA over change in time. Okay, the only thing that's changing up here is the magnetic field. Okay, uh, low magnetic field, the Earth's magnetic field. Remember that was like 5 times 10 to the minus 5 or something like that. Very, very, very low. This is 2. Okay, 5 times 10 to the minus 5 is what, 0.0005 or something like that. So we can ignore that one. So 2. So it went from 0 to 2 Teslas. That's your delta B. 0 Teslas to 2 Teslas. And we found the area up here. And then it was in 0.25 seconds. So we got 3.04 millivolts. Okay. Okay, this is number 12 in Urone. So that's how much voltage was induced in that ring. Okay, number 12 in Urone is 0.250 radius, 500 turn coil. Remember, we didn't have the end up here because it's just a ring. It's just one loop. Here we got a 500 turn coil rotated once, 1/4 of a revolution in 4.17 milliseconds times 10 to the minus 3 seconds, originally having its plane perpendicular to the uniform magnetic field. Okay, this is 60 revolutions per second. Find the magnetic field strength needed to induce an average EMF of 10,000 volts. Okay, so we know, again, it's back to this guy spinning in the field. It's back to these guys. Spinning, this guy here. Oops, darn it. This guy here is spinning, okay? So we know what it's spinning like, and we know all that stuff. What we want to do is find out what magnetic field strength do we have to get that 10,000 volts we want. Okay, so again, we'll go with the maximum. So we've got the N out here, the number of turns, we know that's 500. The change in the magnetic field, the change in the area. Okay, area is going to be equal to 2 pi r. That's that value right there. Okay, so the area doesn't change. It's just the magnetic field that's changing. So we solve for the magnetic field. So we solve for the magnetic field here. So you've got the E delta T divided by the number of turns times A. So you want your 10,000 volts, and you know that that thing's going from no flux through it to maximum flux through it. That's the whole idea. It's going from 0 to maximum magnetic field in 4.17 milliseconds. There's your turns, there's your area from up here. And so you're going to want a magnetic field of 0.426 Teslas. Again, so you want 0.426 Teslas here because this guy goes from being parallel to the field, in which no flux passes through it, or well, I'm sorry, yeah, the area goes from being parallel where no flux passes through it to being perpendicular where all the flux passes through it. But that goes from cosine, that vector that is perpendicular to the area, that goes from being 90 degrees, so cosine of 90 degrees is 0, to 0 degrees between the perpendicular to the area and the magnetic field. So then you got maximum. So that was the change in the magnetic field from 0 magnetic field to the maximum magnetic field. So your change in magnetic field is simply the 0.426 Teslas. You put that many Teslas in there, you've got it going so that it goes that spin, that quarter spin, in 4.17 milliseconds. You've got this area here. Then you're going to induce 10,000 volts for that'll be the maximum voltage at that point. Okay, at what angular velocity in revolutions per minute will the peak voltage of a generator be 480 volts? If it's 500 turn, that's N equals 500, 8 centimeter diameter coil rotates in a 0.250 Tesla field. All right, so we use this guy here because we want the peak voltage. So peak means everything's maximum. So we go with E0. We don't worry about the cosine or the sine. I get the sine in this case. Sorry, the sine in this case. E0 equals NBA omega. We find the area. Okay, we found the area right here. We solve for omega. Omega equals that maximum EMF, which is 480 volts, divided by N, 500 turns, B, which is the 0.25 Teslas, area we found up here, and we get 764 radians per second. Well, they asked for revolutions per minute there. So here you go. You have 764 radians per second, and there's one revolution for every 2 pi radians, or 60 seconds for every 1 minute, and we end up with 7.30 times 10 to the third revolutions per minute. Okay, what is the peak EMF generated by a 1,000 turn, 20 centimeter diameter coil in the Earth's 5.00 times 10 to the minus 5 Tesla magnetic field, given the plane of the coil is originally perpendicular to the Earth's field? So if the plane is perpendicular to the Earth's field, it's rotated parallel to the field. So perpendicular to the Earth's field is when the maximum amount, so we're actually going down here, but we're changing the magnetic field, okay? So if we have 2 pi, let's see here, what is the peak EMF? So we got that coil, blah, 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 give it a plane, so it'll be rotated parallel, okay? So it's to be rotated from being perpendicular to parallel, that's a quarter of an entire turn. So so 2 pi is an entire turn, pi is half a turn, pi over 2 would be a quarter of a turn. That's why we have pi over 2 here, and we did it in 0.0100 seconds. So we end up with 157.08 radians per second, okay? So now we've got everything. There's your 1,000 turns, there's your magnetic field, that's the maximum, the peak EMF, so then it's going to be maximum magnetic field. Your problems on the exam will be just like this. 0.0314 meters squared is the area which we were given, or what? Wait. Okay, we weren't given it. I must have figured it out some other way. But I mean, I just did. We were given the 20 centimeter diameter, so 10 centimeters, 0.1 meters squared times pi. Okay, that's why you got the 0.1 meters squared times 3.14. It'll be 0.01, right? Yeah, 0.01 meters times pi. So you can do that in your head now that I think about it. 3.14 times 0.01, you're going to get 0.0314. All right, and then you got the radians per second here, and you're going to generate 0.247 volts. Okay, an American traveler in New Zealand carries a transformer to convert New Zealand standard 240 volts to 120 volts so that she can use some small appliance on her trip. What is the ratio of turns in the primary and secondary coils of her transformer? Okay, so basically it's just, remember this, we got that? Voltage secondary divided by voltage primary equals number of turns secondary, number of turns primary. So you just take the ratio. So she's got to have 2 more turns. What is the ratio of turns in the primary? The primary has twice as many turns. It could be 2 to 1, it could be 4 to 2, it could be 10 to 5. But it just has to have twice as many to up the voltage, or actually, up the voltage from 120 to 240. Okay, what is the ratio of input to output current? Input current is the primary current, output current is the secondary current. So you got the same thing here. You got IP over IS equals NS over NP, and so that's the same as 1 over NP over NS. So we just found out what NP over NS is here. That's like a weird way to do it, but anyway, you got 1 over 2.00 or 0.500. So in other words, she would have stepped up the voltage from 120 to 240. I said that wrong. She's stepping down the voltage. She gets 240 volts out of the outlet, but she wants 120 volts to run her American-made appliances, okay? So the secondary, she wants 120 volts, okay, I've been going straight since early this morning, so I'm really tired. I'm confused here. Seems to me like 240 to 120. 240 should be the primary voltage and 120 should be the secondary voltage. That's not what I have here. So let me look at this. I'll come back to it tomorrow. But it's the same old deal, okay? And then let's go on. Okay, here's one. Okay, so what is the voltage output of a transformer used for rechargeable flashlight batteries. If its primary has 500 turns, its secondary has 4 turns, and the input voltage is 120 volts. So we have this again, the secondary voltage, which we're told the input voltage is the primary voltage. Okay, so we want to get the secondary voltage, the output. Okay, so this one makes sense. All right, so we solve for the secondary voltage. We want this output is what we want to find out what we have, okay? And we're input voltage, that'd be the primary, that's 120 volts. So here we got 120 volts. We've got the number of turns for the secondary is 4, it says it right there. The number of turns for the primary is 500, so there you are right there. So you got 4 divided by 500 times 120, so you're going to have 0.96 volts. That's what you would get out of that transformer. Okay, you're stepping the voltage way down. What input current is required to produce a 4 amp output? Okay, so the input current is going to be the primary current. The output is the secondary current. Okay, and we want an output of 4.00 amps. All right, so if we have IP over IS equals NS over NP, that means IP equals IS times NS over NP. We already know that NS, the secondary is 4, the primary is 500, okay? So 4 amps, that's going to be the output, times this is going to be 32.0 milliamps. Okay, so there's that one, and then what does the last one say? What is the power input? Well, you just take the input current, the 32.0 milliamps, times the 120 volts. That gives you 3.84 watts. How much more is there? Oh, this is another more of the same. Plug-in transformer for a laptop puts out 7.50 volts, so that's the secondary voltage, and can supply a maximum current of 2.00 amps. Okay. So what is the maximum input current if the voltage is 240 volts? Assume 100% efficiency, okay? So you just take your primary current divided by your secondary current equals your secondary voltage divided by your primary voltage. Solve for primary. That's going to be secondary times Vs over Vp. So you got your 2 amps from here. You've got your secondary, the 7.5 volts. That's what it puts out. The input voltage was 240, that's the primary there. And you get 62.5 milliamps. If the actual efficiency is less than 100%, would the input current need to be greater or smaller? If the efficiency was less than 100%, the input current would need to be greater because more power would need to be put into it in order to get account for the losses. Because in that case, you're saying you're getting losses. Okay, chapter 24. Okay, we'll do that one, those tomorrow. All right, so the plan is just, this is everything, okay? Here's your 24, a couple of problems. Here's your 25, that's it. Okay, just a few more problems. The PowerPoints for those guys are not long. What is this? 1, 2, 3, 4. This is 24 has 7 slides, and 25 has 12 slides, but see, I put out all of the index refraction, so that takes up way more space, so it's not really that bad. Okay, so you can look these over, and then I'll put out a video tomorrow. Also, another thing I want to do is maybe for a review for the exam is to kind of go through. I have some labs that are going to be very, very easy. I'll actually put out a video that shows you how to do them, where you just have to do one more little step there, and I can even make those do after the exam, after the final. So, but you can do them before the final. But they'll be easy, and I'll put out a video that'll show you how to do them, and it'll be kind of a review type thing. Okay, I think that is everything. So I'm going to start uploading this using the SAC state system, which means it might get up pretty fast. I'll see, and then I'll talk to you tomorrow. Oh, and another thing, I'm going to schedule a Zoom meeting for tomorrow at 12 and for Wednesday at 12. So both days at 12 o'clock. I didn't do one for today because I would have told you so late. So I'll go ahead and put a Zoom meeting up, a Zoom for tomorrow and for Wednesday as well. And then the final exam is on Thursday. Okay, so I'll talk to you later. Good night.